Hello, this is Mr. Manley, and I am going to look at a vector application problem here that involves a weight here of 20,240 pounds that is being held up here and here by two cables that are at particular angles to horizontal. If I take and make a horizontal line here, that's what this 24.3 degrees is. And if I continue that horizontal line here, that's what this 44.5 degrees is. And what our question is how much, essentially, how much of the weight is being held by this cable and how much of the weight is being held by that cable. More precisely, what are the tensions on the right, which I'm going to call T sub R, and the left, which I'm going to call T sub L. Here is an approach to this problem. You can certainly see different approaches, and if you take a physics class, they probably definitely have a different approach than what I'm going to do here. I'm going to do an approach that uses a little bit of vectors, and then it's going to have some trigonometry, and I need to talk about the physics of the problem a little bit as well. And I'm not a physics teacher, so don't hold me too much. I know just enough to get me to the point where I can do the mathematics to solve the problem. What is happening physics-wise here is that this weight is acting down like this and creating a tension in these two cables. Each individual cable has a horizontal component that is pulling horizontally and a vertical component that is pulling up to produce a resultant tension in the cable. So did you follow that? I'll do it with another color here, that I'm going to the right. If I'm looking at this one on the right, okay? So I'm going to the right and up, and if I get those two vectors, the sum of those two vectors gives me this vector. And then the same thing is happening on the left as well. So I'm pulling to the left, and I'm pulling up, and then that is giving me this result. And what is happening here is that I can break these two pieces on the triangle, the horizontal piece and the vertical piece, and let's label those. Let's call this on the right, I'm going to call it the tension on the right horizontal, and then I'm going to go the tension on the right vertical, and I'm going to take the tension on the left horizontal, and I'm going to take the tension on the left vertical. So a couple of things are going on here. One is that the tension on the left vertical plus the tension on the left horizontal is equal to the tension on the left. And that's just the way the vectors are behaving. That's the addition of a couple of vectors to get a third vector. I could do the same thing on the right. That actually, it turns out, that's not a useful equation for us. It's nice to understand how things work, but it's not the equation that is going to help us solve this problem. What is going to help us solve this problem right at this point is now to figure out some substitutions for, well, actually, before I do the substitutions, let's say something else that we know, which is useful, which is that the vertical tension on the left, T sub LV, plus the vertical tension on the right is equal to 20,240. So let's get in here with a little highlighter or something and go, look at the left. So this on the left, that on the left, plus that on the right. The sum of those two vertical tensions has to be strong enough to hold up this 20,240 pounds. So the sum of these two has to be 20,240. Exactly. If it were more than that, then this weight would be moving up. And if it were less than that, the weight would be dropping down. But at 20,240, these are holding the weight. The two cables are holding the weight stationary in its position. Then another relationship that we have is that the tension on the left has to equal the tension on the right. So this tension here on the right and this tension here on the left, those have to be equal. The horizontal tensions, I should say. The horizontal tension on the left and the horizontal tension on the right have to be equal so that the weight doesn't move. It's not moving from side to side. It is, again, stationary, but unlike the action of the weight itself, which is acting down, the weight isn't acting right or left. There's no sort of force that is being exerted to the right or left. So all I've got is that the tension on the left has to equal the tension on the right, and this represents the weight being horizontally stable or stationary. All right, now at this point, look at the equations. I've got 1, 2, 3, 4 different variables. So remember that. That's the key here, is that I've got 4 different variables, and I can't, so there's nothing I can do with that. But what I can do, watch this neat little trick, is I can take let's just take one of these triangles. If I take this triangle on the right, okay, I'm going to take that. And what I want to do is I want to use some trigonometry here to say some other things that I know about these two values here. And it's very simple SOHCAHTOA trigonometry that I'm going to use. I'm going to say that the cosine of 44 degrees is equal to adjacent, which is TRH, over hypotenuse, which is TR. And then I'm going to, so I've got this measure on that horizontal part of the triangle, right? Well, there it is there. Now I'm going to solve this equation. I'm going to solve this equation and say, therefore, I've got TRH is equal to TR cosine 44 degrees. Missing the 0.5 in both of these. So there, that's 44.5, 44.5. No big deal. Okay? So now I can take this guy here. This is equal to this. So that's what the horizontal part of that is. So let's write that in. And so we can say that this horizontal piece is equal to T sub R cosine 44.5 degrees. And then the vertical piece, this piece here, I can say that TRV is equal to, well, I can't say that yet. Let's do, say it like with the SOHCAHTOA trigonometry again, that the sine of 44.5 degrees is equal to opposite, which is TRV. So you can see that, right? The opposite side to 44.5 degrees is TRV, over the hypotenuse, which is TR, and then again, I can solve for TRV and get an expression for TRV that I can put on the vertical side of the triangle, right? So let's go ahead and write that in. So now I can say that this is equal to TR sine 44.5 degrees. And then without actually going into any detail, you just follow the same process. If I can do this on the right and say that the horizontal component is TR cosine 44.5 degrees on the right, well, guess what I can do on the left? I can pretty much do the same thing. And if you need to look more at the triangle and do the trigonometry, you can do it. But, I mean, can you see how it makes sense if I just say TR cosine 24.3 degrees on the left? And then I'm running into a little space issue here, so I'm just going to draw an arrow to that side of this triangle on the left and say that that is TR sine of 24.3 degrees. So do you see how that correlates? TR sine 24.3 degrees on the right and TR sine 44.5 degrees on the right. Or on the, I keep saying the right, but it's the left on here. So this guy here, TR, that's TL, okay? Because I'm on the left at this point. So let's get that fixed up there. And I've got TL there, okay? And I made the same error with this guy here. So that's not TR on the left, that's TL, because L for the left. So let's fix that up. And I've got TL on the left there. Okay, now, can you see what happened? I've got this TL for TLV, and I can substitute that. So I can substitute for TLV. And then you see also that I can substitute here TRV with this TRV over here. So it's a bunch of substitutions that I can make now. So I'm going to make those substitutions. Okay, so here are all of my substitutions down in this red box down here. And let's really look closely in there. Well, you want to make sure you can see the substitutions that I did. Hopefully that's not too difficult. Just if you take a look at, there's TLV, like I said already, and there's TLV, so I can make that substitution for TLV, which I did right there, okay? So I did that for all four of these terms here. This term, this term, this term, and this term. I did all of those substitutions for those. And now, with those substitutions, take a look here. Look at my variables. I've got TL, TL, TR, TR. So I've got a system of two equations with two variables. Hopefully you understand that if you have a system of equation with two variables and two equations, you can solve that system. It's really going back to a basic algebra, like if I had 3x plus 2y equals 7 and 2x minus 2y equals 10, you can solve that system for x and y. Same thing here, it's just we have a little bit of trigonometric evaluation to do, which is no big deal. So I just have to, it's just a calculator key in to go, what's the sine of 44.5 degrees in order to get my coefficient for that TR term in this equation. Really, the simplest thing to do at this point, I would say, would be to go ahead and take here, divide by 24.3 degrees. So I'll just do that. Well, I'm not going to do the calculation, but I'll look at the setup. And I'm going to divide by cosine 24.3 degrees. So that'll cancel over here on the left. Now I've got TL in terms of TR, and I can do that substitution. So I can substitute for this TL, and then I'll have an equation in one variable, TR, T sub R. And you can solve for that, certainly. So there's a problem. Just note that we talked a little bit about vectors. We talked a little bit about some trigonometry, really geometric type of trigonometry, right? SOHCAHTOA. And then we looked at a little bit of physics. And I'm not going to go through the details of solving for TL and TR. Yeah, you should be able to do that at this point, and hopefully you can apply this technique to another similar type of problem.